And thank you all for coming, and thank you to IEPC organizers for having me. It's a pleasure. It's my first time in this conference, first time in Berlin as well. I'm enjoying it a lot. And this talk is called Build Your Own Neural Network with PHP. So today we are going to build an artificial neural network from scratch using good old PHP. And yes, that's possible. So first, just a few things about myself. I'm Vitor. I'm Portuguese, as you can tell by my accent. But I'm working as a software consultant now in the UK. So if you do follow my Twitter at Noise Labs, heads up, that's 90% Brexit tweets. I don't recommend it. But if it's instead you go to my blog, noiselabs.io, I can guarantee that one is 100% Brexit free. And now a few disclaimers, because I have to start with those. So first one, I'm not an expert. I can see someone laughing. I'm not an expert in this field. I don't have experience with AI or machine learning production, and as such I wouldn't be able to give you industry advice. Just consider myself to be a student. Second, there will be math throughout the talk. Sorry about that. Or to be more precise, oversimplified math. And I hope it's not too scary and you just stay throughout the talk and do not leave, hopefully. And the last one is that there is a lot to cover in this topic. There are a lot of slides, so I'll be going fairly quickly. But if you have any doubts on some slides, please just raise your hand and I'll stop and I can clarify it right there, okay? Yeah? Okay, so the reason why I'm giving this talk is because AI and machine learning is all the hype these days. I mean, you can barely go one day without hearing about machine learning in the news. And the trend is growing. And AI is everywhere, and it's kind of magical. I guess the only thing more hyped than AI is blockchain. But about that, I know pretty much close to nothing, so you have to find another talk and another speaker for this. Now, the second reason why I'm giving this talk is because it's kind of rare to see PHP and machine learning together. And I think we deserve our fair share of AI. And also, if you're trying to learn something complex, such as machine learning can be, then I think it makes sense to pick a language you're already comfortable with, such as PHP, if that's your primary language, and then learn the other complex thing, which would be machine learning. I think that makes sense. So, AI is used pretty much everywhere. You can see it on speech recognition, handwritten recognition, automated trading systems, and the recommended systems that you see on Amazon or Netflix, even though sometimes you wonder what kind of AI is there based on those recommendations. So AI will be driving us soon everywhere. It will be our doctors, it will be our lawyers, it will even replace us as programmers. By the way, this is a pretty cool article. There is a link at the bottom. Check it out. The slides are already online. It's really cool. Maybe you can use it and still charge your client. And if you have enough free time, why not use machine learning to put Nicolas Cage's face on films such as Indiana Jones or The Lord of the Rings? Instant classics. Now, at the foundation of many of these AI applications that we have just seen, we have artificial neural networks. So today, we're going to see why are they called neural networks, how do they learn, how can we write one using our favorite language, for some, and what the hell is deep learning? So, without further delay, let's start with the light topic. the human brain. So this is a picture of a brain, half of it. And in a full brain, you can see you have 86 billion neurons. And the neuron, which looks like this, is a cell that transmits information through chemical and electrical signals. So you have the dendrite that connects to the previous neurons, where the signals arrive. Then they are processed in the cell body and the nucleus, and they flow through the next set of neurons through the axon. So another way to look at this is to say that our dendrite is performing some sort of input. Our nucleus is an activation function, and the axon can be, we can say it's the output for this neuron. So in 1943, McCulloch and Pitts, inspired by this biological model, they developed a mathematical model which became the first artificial neuron. And it looks something like this. So this is another representation of the neuron. So let's say we have two inputs. So it's connecting to two previous neurons. Let's say it's X1 and X2. And each connection is affected by a weight, W1 and W2. And then within the cell, we perform this sum. So we multiply weights times X, which is our input, plus the bias. And the weight and the bias is what we call the learnable parameters. So the weights, they are the influence of one neuron on the next one. So the connection can be thin or thick. The bias is an addition term that allows us to shift the signal, output signal, left or right, so that it matches our desired output. So these are our learnable parameters. So that sum plus that sum will then be passed through a function, an activation function. And we get the output for that neuron. So we have input, and A will be our output. This is what's happening in a mathematical model of a neuron. So in summary, for two inputs, this is what's happening, W1 and W2 plus B equals Z. We pass Z through an activation function, and we get neuron output. Activation function models the firing rate, is used to model the firing rate, and most importantly, it adds nonlinear capabilities to the network. And we're going to see why that matters, why that's really important later in the talk. So a very common activation function is the sigmoid function, which is this S-shaped function. So for large negative numbers, the output will be 0. And for large positive numbers, the output will be 1. So the output will be always between 0 and 1. This S-shaped function, the sigmoid function. So if you have another look at our neuron, and if we zoom out, then there you have it, our very first neural network, very simple neural network with just one neuron, one output layer, because funnily enough, input layer doesn't count as a layer. So one output layer, one neuron, and two inputs. Now, it does that funny sum, and it goes through an activation function and whatever, but how does it learn? I mean, how does it do something interesting? And the answer is by using machine learning. And in this case, specifically, supervised machine learning. So what is machine learning? So in machine learning, we have a set of known inputs. So there are known inputs X, and we have a set of known outputs Y. And what we want is to learn a function that maps X to Y. We don't know the function yet. We need to find it out. So that once we have found out that function, we can throw it new inputs from the same data set, and we can see some very good predictions that we can trust. So that's the basis for supervised machine learning. And this is a departure from traditional programming. So in our programs, in our traditional programs, what we do is we write the rules, we write the routing, if statements, and we give it some data, and we get some answers back. That's how programs work, basically. But with machine learning, what we do is we throw it all the data, we give it the answers as well, and then the system will figure out the rules, which I think it's pretty neat. So if we have another look at our neural network, we can see that this one, with just one single neuron, is able to solve linear problems, such as this one. So it can find out this function, and if we ask it to predict a new value, it will say it's over there. But most interesting problems are non-linear. So what we have to do, we have to upgrade our network. And we do that by adding a hidden layer. So our network now becomes this. And now I have 2 layers. Because again, input layer doesn't count. I don't know why, that's how it is. So there we have it. A neural network that is able to solve non-linear problems. And that's why, because when the activation function is non-linear, such as the sigmoid is, then a 2-layer or bigger can be proven to be a universal function approximator. And that's why it makes them so powerful, because they can, in theory, represent any function. So let's have a look at what the training approach, the learning process, is going to be for this artificial neural network. So we're going to start with random weights. Then we're going to make a prediction, which I say it's y hat, based on my input data. It's going to be a random prediction. And we're going to compare that prediction with my known input, my answer, the thing I know it's right, y. And then, based on the difference, I'm going to adjust my parameters, my learnable parameters, w and b, and then I'm going to repeat that until we are really close, and I say I have a good function that maps my inputs to my known output. So this is what we're going to do. Now, let's say you're going to build, an app to classify cats, a cat classifier. Why not? You could make some money on that. To do this, you would have to collect a bunch of pictures of cats. That's your data set. And you would label that with a 1 for it is a cat. And then you would get a bunch of other pictures, other animals, even objects. And then you would label that with a 0 for it's not a cat. You would feed those images, all your data set, with your labels into your network. By the way, that's just decomposing the RGB image into an array, a vector. And you would feed that into your neural network, you'd keep it training until you get a good function, and then if you'd send it a new picture it hasn't seen before, and you'd get an answer of, say, 0.73, you could say, yeah, it's pretty close to 1. Okay, I think it's a cat. Now, as much I would like, and as much I would love to teach you how to build a cat classifier, that's not possible in just 45 minutes. So I'm sorry to disappoint you, but we're going to see an XOR instead. And just a quick reminder on the XOR. For XOR, looks like this. So for equal inputs, you get an output of 0. For different inputs, you get an output of 1. So that's my inputs and outputs. That's my data set. It's really small, but it's enough for this talk. And so if I put this on a chart, you can see that there is no straight line where I can separate my zeros from my ones. So my very simple neural network, which can only solve linear problems, is not good enough for an XOR. It sucks. So for that, I need this one. So with a hidden layer, now I'm able to solve nonlinear problems, and my network, which is the one that we're going to code, looks like this. Okay? So as you can see, x1, x2, my known output, my bias over there, and then each connection, each neuron is connected, and for each one I have an associated weight. So it's fully connected, and this is an example for the feed-forward neural network. There are a lot more topologies. This one is a feed-forward neural network, and it's good for an XOR. So with this information, we're now ready to start coding. By the way, all the code that I'm going to show in the next slides is available on GitHub. It is a fully working example, so don't worry if you miss some details on the next slides. You can just check it out, run it locally. I think it even runs on Docker, and just don't worry, you'll be able to play with it after the talk. Okay, so let's start with something predictable, let's say. Let's write a class called neural network class, and in this class I'm going to have two methods. The train method for the learning phase, and a predict method for when I want to make predictions on new unseen data. Okay, and so for the XOR example, I'm going to have my data set with 4 training examples, and for each one I have my answer below. They just match. And I can now instantiate my neural network class, which does pretty much nothing at the moment. So let's go to step number 2. Let's define our topology. So you've already seen this. We have 2 inputs. We're going to have 2 hidden neurons, and because it's just one hidden layer, 2 layers, hidden and output, and 1 output. So this is my topology. So I need to store my parameters as well. So in my class parameters, I will store weights and bias, Z and A, which you already seen on that neuron diagram. And I store that in my variable P. I know we shouldn't use short-term variables, but I think you can excuse me on this one. Now, I could be using to store my WB, Z, and A, I could be using nested arrays and associative arrays to store all of that. I actually done that, and it turns out it's pretty much a nightmare. So there is a much better data structure. Can you guess what it is? What about now? Yes. It's much better, much cleaner, makes total sense, and that's why it's actually used in data science and machine learning. So with a matrix, what I'm going to have is W1 and B1 stored like this. So as you can see, connections coming into the first neuron on the first row, connections coming to the second neuron on the second row. Same for B1. And the same goes for the output layer, because it's just one neuron on the output, it's just one row. So with this, and to implement my matrix, I'm not going to write any code. There is a pretty good library called MathPHP. It's very, very complete, actually. I recommend it. So with this library, I can declare my matrix as an array of arrays, and then I can create the matrix using the helper, and then I can add matrices, multiply it, do a Hadamard product, which is just an element-wise multiplication, and I can go to each element in the matrix and just apply a function, any function. So, quick note on vectorizations. So other languages and libraries, such as Python and NumPy, they do offer vectorization, which is a very efficient way of multiplying matrices. To the best of my knowledge, PHP doesn't have this, and that's why it makes it slower when compared with its other libraries. But I found this PHP extension, which is PHP SCI. I think it's an extension. Yes. PHP SCI, which they promise, by the time I took this screenshot, they said 2,000 times. Last time I saw it's 800. Maybe because just vanilla PHP got faster. And they promised that array operations as multiplication is going to be much quicker. I haven't tried it yet, but please do. I think there is some hope for PHP. So next step, the activation function. So if you remember, the sigmoid function, which is defined by this equation. And by the way, you can have different activations functions. The sigmoid just happens to be a good example for the XOR. So in my namespace activation, I'm going to write a class sigmoid, and then I'm going to just implement that equation. Pretty easy to do. And then I'm going to write my compute function, which applies in a matrix. And then for each element in the matrix, I just call the method below. And there we have it, a class that calculates the sigmoid on a matrix. I just set it in my constructor. That's my first parameter. And now for the training phase. And this is the algorithm that I'm going to use. So, I'm going to start by initializing weights and bias. And then in a loop, what I'm going to do is, I'm going to set a maximum number of iterations, because I don't want this stuff running forever if it goes bad, or until my error, the network error, is above my desired maximum error. So if the network keeps running for a long time, it will be stopped by iterations. If it works, it will stop because the error has fallen below. And then for each training example, so in the XOR, we have just 4 training examples. In the cat example, you'd have a load more training examples. For each training example, what I'm going to do, I'm going to call this 4 steps. I'm going to do a forward pass, then I'm going to compute the cost, then run a back propagation step, and I'm going to adjust my weights and bias and try again. Keep this in a loop. And this is the learning process for my neural network. So step number 1, initializing the parameters. So I'm going to write just a function, and what I'm going to do is for the hidden layer, I'm going to initialize my bias to 0. That's what I'm going to do. And for the weights, I'm going to initialize it with a value between 0 and 1, random value. And for the output layer, I'm going to do exactly the same. Bias is 0, weights, random value, 0, between 0 and 1. Why 0 and 1? Because it just happens, because of the sigmoid function that I'm using. That's a really good strategy to keep values between 0 and 1. And random initialization is also a very good practice when initializing a neural network. So I'm going to call this in my constructor, and it's called only once. Only one creating the network. So this is the initial state of my neural network. So as you can see, random values on all the weights, and the bias are 0. So this is what the neural network looks like when it starts. This is just the initial state. And now for the training method, first step is I just convert my inputs and targets into a matrix, because that's what I use inside. And then I'm going to set some constants. So I'm going to say that my maximum error is going to be not 1. And I will let my network train until it reaches 20,000 iterations. If it got to this number and the error is still above, I just assume that it failed to learn. Maybe the error is still going up again and not decreasing like I expected. So this is just a safe switch. If it gets to that point, things have gone bad. Let's stop it, not burn more CPU cycles. And the original error is going to be infinite. That's my starting point. You obviously can play with these numbers, and other numbers make sense for other examples. So this is the skeleton for my training step. So the outer loop, and then the loop for the examples. And then below, I just keep track of the error for that. I think it's gone off. Maybe the projector? It's still showing on my screen. I'm just going to plug it in again. Yeah. Okay, we're back. It seems like I have, 15 more minutes because it time's out. Okay, so next step, forward propagation. I'm going to use the same equations from the original example. Just now, it's going to be in matrix format, hence the capitals. So for the hidden layer, w times x, and then pass through my function with this sigmoid. It's this symbol right here. Okay, so that's my activation function. And below, the only difference is that I'm going to use activations from the previous layer. So I have the input, and the input for the next layer is the output from the previous layer. Make sense? I could have more layers. It just works like that. Okay. So that's my generic formula for that. For the hidden layer and for the output layer. So if I do the forward propagation step, what I'm going to do is I'm going through in a loop. I'm going to calculate my z using the formula, the previous formula, and using the helpers from that matrix library, such as multiply and add. If you'd had to do this with arrays, it would be like 200, 500 lines just to do that. And you would mess it up. And then I keep activation functions, and L is just to keep track of my layer. It's just an index. And last one is I return the output for my network, and that's actually my prediction. So what comes out from the network is my prediction. And so this is what's happening in the forward pass. I get my inputs, which in XOR is 0, 0. I flow through the network, and I get the value back. And that's my first step in this loop right here. So if you have a look, so as you remember, I've initialized my network with random parameters, and I gave it the first example, which is a 0, 0, and my network told me this is 0.61. Is it a good answer? What do you think? No. Well, let's find out using some math, of course. So I need a compute cost, and I need to use a cost function. I'm going to pick a pretty common one, mean square error, and which is actually quite simple. It's just output minus the prediction squared. That's it. So if I go and write a function, my class mean square error in my cost function activation, because you can use different classes for this if you want, I'm going to compute, and it's so simple. Just target minus prediction squared. That's it. That's my second step. Actually, I'm just initializing it here. And that's me calling the cost function in my compute cost, which I'm going to add. So that's my second step there. And I keep track of it in my costs array. Okay, so that's the second step done. And so if I have a look, so my known output is 0, actually gave me 0.61, which is crap, squared equals 0.38. That's my network error. That's how good or bad the network is behaving. So what I hope is that it starts with a really high error. Why? Because the initial weights are just random. And over time, as it starts adjusting the weight and bias, it will slowly go down, goes below my error, stops training, and I'm happy. That's hopefully what's going to happen. And for that to happen, for the weights and bias to be adjusted, I need this magical step, which is called backpropagation. It's the most scary one. Any questions so far? Everything's pretty clear then. Okay, so backpropagation is a supervised learning method for this kind of feed-forward networks. And it uses gradient descent. So what it's going to do is going to look at the gradient of the error function, which is actually the loss function, with respect to each learnable parameter, so the weights and bias. So here's a scary slide for you. Who has done or remember partial derivatives? Everyone then. Okay, so basically this is what's happening. What we're going to do in backpropagation is just look at each individual weight and bias in the network, okay? And we're going to look at how much it contributes to the overall error. Each individual weight and bias, I'm going to see, if I adjust it slightly, what happens to my error? Does it go better? Does it go worse? That's what's happening. That's the partial derivative. That's what's happening. So if I put this in equation, I know it's going to be a bit scary, but the PHP part is not that hard, actually. So for the output layer, it's in a special case. My starting point, I'm going to use dA, is the derivative of the loss function. And then I'm going to calculate dz, which is the previous step, element-wise multiplication with the derivative of the sigmoid function, dw, dz times a, db, just dz. Okay, so that's the output layer. For the hidden layer, the starting point is slightly different. So I'm going to use dz from the previous step, this one right here, and I'm going to use the weight matrix from the previous layer. That's my starting point for the A. The rest is exactly the same. So this is just a special case for output layer. The rest is exactly the same. You could have 10 layers. It will be the same. Just repeat, put that in a loop. Easily done. Okay, let's see that in code. So I'm just going to add 2 more parameters, dw and db, because I'm going to need that. And let's look at the derivative for the loss function, which is basically 2 times prediction minus output minus prediction. Pretty easy to implement. So I'm going to add a second method on my mean squared error class. So it was already doing compute for the forward pass, and now it will do differentiate for back propagation. It's just this times 2, and that's it, and we get the matrix back. For the sigmoid, it's actually quite easy as well. It's just the sigmoid itself times 1 minus the sigmoid. Not that hard. Differentiate method, I'm just going to call the sigmoid again, times 1 minus the sigmoid. And that's it. So compute method, differentiate method in my sigmoid activation function. So once I have those, I'm just going to start with output layer. So as you can see, calculate dA, just calling differentiate on my loss function. And then I'm going to do dz, Hadamard Proget, because that's element-wise multiplication, dw and db. And then if I go for the hidden layer, exactly the same thing. It's just dA is slightly different. But then I can calculate dz and dw and db. You can have a look later on these details. So here we have my do back propagation step. And the last step is update parameters. So for update parameters, I'm going to use gradient descent. And for that, this is how I'm going to update my W. So the new W, the new weight, is going to be the current weight minus TW, which I've stored in a PHP variable, times alpha. And alpha is the learnable parameter. And for B, it's exactly the same, but I'm using dB instead. So the learnable parameter, alpha, allows me to control the jump between each iteration. So if alpha is too big, the jumps are too big as well, and I might miss, this is the error, I might miss the optimum value for the error if the learning parameter is too big. But if the learnable parameter is too small, it will take a long time to converge. It will take a long time, and it may even miss the optimum value as well. So there is a sweet spot for the learnable parameter. So that's what I'm going to do here. I'm going to say my learning rate is going to be 0.1, where you can play with this. It's just a fixed value that I'm going to put there. So to update parameters, I'm just going to every layer, calculate the new W based on the previous W, times my learning rate, and same for P. And that's my last step. And finally, I just keep track of the error, because I need to know when to stop above. Okay? So this is the full code for the learning in a neural network written in PHP. That's the full code for that. And with this, training complete. The worst part is over, by the way. No one left yet? So I guess you can stay till the end. Okay, so just recap. So algorithm for training. I started with initializing weights and bias randomly and also to 0. I've set some conditions for when to stop because I don't want this running forever if it has no point. And then for each training example, I just do those 4 steps. I do forward pass from the beginning, goes through all the end to the network. I check the error on compute costs. I apply some magic using backpropagation and derivatives. Back to the beginning, I adjust my weights and bias, keep looping until weight and bias get to an optimum value. So this is an example taken from the TensorFlow website, which is a Python framework for machine learning. And hopefully, this is what we're going to have, what's going to happen during the learning phase. So as you can see, some connections will grow stronger, some are a bit thinner, and some neurons will specialize on identifying the blue ones, some other will specialize on identifying the orange ones. So over time, as you can see, it will slowly be able to find some boundaries between the blue and the orange circles. So hopefully that's what's going to happen, and you can see the error dropping right there. So hopefully that's what's going to happen during the learning phase. So let's put this to the training. So I'm going to call my script, and epoch is just a number of iterations. So after 1,000 epochs, I get an error of 0.22, almost 0.23. But 400 iterations later, it has dropped 100 times, actually. Quite good. It's going the right direction. And around 10,000 epochs, it has fallen, or is going to fall below my maximum error, which was, if you remember, 0.1. So it stops. And now, if you put this to a test, and I'm going to cheat here, because I only have 4 examples, so I'm going to use the same examples. In real world, you would feed it on something new, unseen. So if to implement predict, it's simply called do forward propagation. Remember now, the network has stopped learning, so the weight and bias, they are frozen. So keep it like gold. Those parameters are frozen, so I just call do forward propagation, and the value that I get at the end of the network, that's my prediction. So if I call it with 0, 0, I get a prediction back of 0.03, which is pretty close to 0, same here. And if I call it with my inputs, which are 0, 1, and 1, 0, I get something that's really close to 1. So I would say this is a success. Okay. You don't have to use the XR. I'll challenge you to pick a more creative example. You'll have more time than just 45 minutes. So go and play with this with something more creative or more useful. Play with different activation and cost functions. As you can see, I've just implemented sigmoid, but there are many other activation functions, the ReLU function, tanh, there's a lot more that you can play with and get better results. You can play with different cost functions as well. And the learning rate, you can play with that. Let's make it train faster. Let's see if it still works. Or I know that with 0.1 it works, but what if we use just 1? Maybe it just converts after 1,000 iterations. And if you do that, you can open a PR on this repo that I've shared before. And why not try with different topology? I've used 1 hidden layer. Why not use, I don't know, 2, 5 hidden layers? How does it going to work? Maybe on that 1 hidden layer, you can put 5 neurons, 5 hidden neurons. How does it going to work? And you can even compete a Kaggle, and you can win some prizes. It's a data science machine learning competition website. Check it out. So, quick recap on what we have seen today. Neural networks are inspired by the human brain, but actually today is more of a mathematical challenge and engineering challenge. It's diverged a bit from biology. And we saw a feed-forward network, but there are others. So if you'd go and, let's say, use something for video processing, just an autonomous driving, then you'd use convolutional networks, which are a lot more complex and wouldn't fit in the screen. Or for speech, you could use recurrent neural networks, because they look at the previous syllabes and words of what you said. Today we use supervised machine learning, which is just learning from examples, but there is also unsupervised machine learning, in which you don't label data, you just ask it to find patterns in data, to find similarities. So that's really useful as well, because labeling data is a lot of work. There are actually some companies making money just by building the data sets, because machine learning needs large data sets of labeled data. So some companies even make money just taking pictures and putting a label on it and then selling it to companies that actually use machine learning. If you want to do that, why not? And in this example, we have used backpropagation and gradient descent, which I think is the magical bit in a neural network and can be done using PHP. And in theory, as you can see, you can approximate any function if we are using a non-linear activation function, just as a sigmoid, and that's what makes them so powerful. Okay, so today you have seen a network like this. But if you added another hidden layer, or maybe even more hidden layers, and if you kept adding more hidden layers, then you enter the realms of deep learning. So if you see deep learning in an article on the news, is basically neural networks with many, many, many layers, then we can call it deep learning. That's what deep learning is all about. So before I finish, just a few resources I would like to share. So if you're still interested in this topic, the Wikipedia article is quite good on artificial neural networks. There are some really good courses. I think this one was the original course on Coursera. This one is really good, and it covers uses modern tools, but I think it's paid. It covers things such as convolutional networks with autonomous driving and speech recognition, and it uses Python mostly, I think. TensorFlow, actually. The first one is more of theory, but it's really cool. This is one of the heroes of AI, Geoffrey Hinton, so please check out his slides. I would say start with this one because it's a bit hard to digest. And there's so many resources nowadays about machine learning, and they're actually free. Google has a really good one as a crash course on machine learning, and it's very hands-on as well. And last one, which I'd like to highlight, that one, which is really good if you're into the backpropagation step, want to understand a little bit better, more partial derivatives, maybe. And so this book as well, it's not PHP, it uses Python, but it's hands-on, so you see some examples, you can play with that, it's really good. And if you're in a rush, this is a less than 5 minutes video that explains just the neural networks. It's really good. And it's also from the deep specialization course I put on the previous slide. And it's available on YouTube. And with that, I reach the end of my talk. Thanks so much for your patience. And I'm ready for some questions if you have it. Thank you.